Flipped classroom video for Maths A2 Unit 3, Types of Mapping. So, what is a mapping? Well, a mapping is a relationship between two sets of objects. For us, these objects are going to be numbers, but we're first going to look at them in a more abstract way. Now, the word mapping is not formally defined. People use it for slightly different meanings, but the one we're going to use is one that's commonly used in the mathematical context. But be careful if you do come across the word mapping. People use it to mean different things. Now, we can see a mapping on the right. Well, we see two sets on the right, and then the mapping is the arrows which connect various members of the two sets together. And in this case, the relationships are obvious. The red circle is mapped to the word red and to the word circle. The blue parallelogram is mapped to the word blue, and so on. So we suspect that the mappings, the arrows that connect the various items, are based on descriptions of them. But if we change the set B, keep the relationships the same, then it's not at all obvious what the meaning of the relationships are, but it still represents a mapping. The red circle maps to Pob and Croggy. The blue parallelogram maps to Flam, and so on. And we can see that there are some members of set A which map to more than one member of set B. We've just said, in fact, the circle maps to Pob and Croggy. And this means we have some elements in set A which are one element mapping to many elements in the other set. We've also got members of set B that are mapped to by more than one member of set A. So, for example, Flam is mapped to by the parallelogram and the square. And so, this means we have elements where there are many in set A mapping to one in set B, so they are many to one. And because we've got one to many and many to one, then this mapping is a many to many mapping. It means that there's many objects mapping to one from left to right, but also there are many objects mapped to from the first set, from many. Now, number mappings. Rules. We've come across many rules in our mathematics thus far, and they lead to mappings. So, if we look at these three, we would call them graphs, but actually they are mapping x values to y values. So, if we look on the green graph, then we see that the value 2, the x value 2, maps to the y value 2. The x value 4 maps to the y value 3, and so on. So they represent mappings. And for each of these mappings, as I've just said, basically we take x values, we use a formula, we generate y values. We can do it the other way around. We could take y values, use a formula and generate x values. Doesn't matter. But what we're doing is we're mapping from one set of values, the x values, to another, the y values, or vice versa. So we'll have a look at each of them in turn. It happens that the green line is actually a representation of the mapping y equals x over 2 plus 1. And that is a one-to-one mapping. Every value of x maps to a unique value of y. Now, the values we're mapping from, they together form the domain. So in this case, the x values are the domain for this mapping, and for all these mappings in fact. The y values are called the range, and they're where we're mapping onto. So in the previous screen, those shapes were the domain, and then the words, which originally were circle and red and so on, but then became Pob and Croggy or whatever, would be the range. So in this situation that we're looking at now, we're mapping from x, the domain, to y, the range. Okay, looking at the blue graph, and as you've probably spotted, that is a quadratic, so that's y equals x squared minus 2x plus 3. Now this is a many to one mapping. Some values of y are mapped to more than one value of x. In fact, all the values of y that are mapped to, apart from the number 2, which is at the minimum there, are mapped to by more than one value of x. So if we take, say, the y value 3, we are mapping to 3 from 0 and from 2. And if we took the y value 6, that is mapped to from minus 1 and from 3. So this is a many to one mapping. Y equals the square root of x. Now we've got to concentrate hard on this bit because this is very important. This is a one to many mapping. Some values of x map to more than one value of y. Well, actually all the values of x that we're concerned with, which is x greater than or equal to 0, they all map to two values of y apart from 0 itself. So the value 1 maps to 1 and to minus 1. The value 4 maps to 2 and to minus 2, and so on. Now, for a mapping to be a function, it must be either one to one or many to one. In other words, and this is really important, every element in the domain must have a unique image in the range. So in this example, we can't have any x value mapping to more than one y value. What that means is that y equals the square root of x as we're presenting it here is not a function. And one way on a graph anyway that we can see whether something is a function or not is if we can draw a vertical line that hits the graph in more than one place, then we don't have a function. Now, in fact, if we were to define root x as meaning the positive root, then on the graph we'd only get the red part that's above y equals 0, and then it would be a function. And conventionally, when we're dealing with functions, the square root is defined this way. And this is a bit of a confusion. You've already been in situations when solving quadratics, for example, where you have to say, if you have the square root of 4, you have to say that could be plus 2 or minus 2. That's when solving equations. When we're dealing with functions, then unless otherwise stated, we assume we're dealing with the positive square root. Okay, functions, domain and range. So we've touched upon domain and range. In the last example, we had the x values were the domain and they were mapping onto the y values, which were the range. So the full definition of a function is that we need a rule, we need a domain, and we need a range. So, for example, previously we'd be happy to define a function as f of x equals x squared and assume that everyone knows that x could be any old number. Now we need to be more precise. So we could define this function thus. All the colours are telling us is when it's red it's the domain and when it's green it's the range. So we could define it saying f is such that we're mapping from the real numbers to the real numbers, basically meaning any old number to any old number, and it is such that f of x is equal to x squared. Another way we could represent it would be f of x equals x squared such that r is being mapped to r by f. And another way still is that we could represent the domain and the range by sets, then we show the mapping going across, or the rule going across, f of x equals x squared. Restricted domains. Now, x squared acts on any value of x. Any number can be squared. But sometimes the domains are not the whole of the real numbers. They might be restricted by the nature of the rule we're dealing with. So an example of that is that for the rule f of x equals root x, then we have to stipulate that x can be a real number, but x has to be greater than or equal to 0. We can't square root negative numbers. Assuming we're only dealing with real numbers, those of you studying further maths or with a wider interest in mathematics than just your schoolwork will know that we can square root negative numbers, but we have to move into a different set of numbers called the complex numbers. So in ordinary numbers or real numbers, we have to stipulate for root x that x is greater than or equal to 0. Or another familiar function, if f of x is equal to 1 over x, then we could define the largest domain as being x is a real number such that x is not equal to 0, because we can't have f of 0 because we can't have 1 divided by 0, because that's not allowed. Sometimes we might choose to restrict the domain so that a many-to-one function becomes one-to-one. A good example of this is if we have f of x equals x squared, we could restrict it to x is a real number but greater than or equal to 0, in which case we would have the function looking like this. Or we could have it as x less than or equal to 0, and then we'd get the left-hand portion of the x squared curve, if you like. Okay, and there are reasons for doing that, which we will come on to later. If you want a function to have an inverse or an opposite, then you need it to be one-to-one. That's one example of why we might want to do that. We're just going to have a look at notation, and in particular interval notation. You may have come across this before, in which case you can zoom on, but this notation is very useful in defining functions because it's useful in defining the domains and the ranges. The basic symbols you've already met are less than or equal to, greater than or equal to. But there are various ways of showing that we have a range of numbers. We can use those symbols, or we can use other symbols. So if we look at this example, we have the numbers from 1 and including 1. If we have a filled in circle or blob, that means that value is included in this range of numbers. And then up to infinity, and that means we've got the numbers x is greater than or equal to 1. So any number x that's greater or equal to 1 is in this set of numbers. But using set notation or interval notation, we can say that x is a member of, that's that sort of Greek E, the set from square bracket, which tells us the end value is included, from 1 up to infinity. Infinity always has a round bracket because that means the end value is not included, and of course we never get to infinity. Okay, another example. Here we have x is less than 0. It's strictly less than 0, and that's denoted by the unfilled in circle at 0, and then the arrow goes down to minus infinity. That means x is a member of the set from, or the interval from minus infinity up to 0. And we notice we have round brackets for both ends. This one we have x lies between minus 3 and 2, and it could be equal to 2, and we can see that denoted on the diagram by the open circle at minus 3 and the closed circle at 2, or filled in circle. And we can also say alternatively that x is a member of the interval from minus 3 up to 2, round bracket at minus 3 because minus 3 is not included, square brackets at 2 because 2 is included. Then we have this situation where we have two possibilities. X could be between minus 4 and minus 2, or between 2 and 4, and that means x is a member of the set from minus 4 to minus 2 union, or from 2 to 4, and the square and round brackets are as before for that. So that's union, which means or. We could have two sets which overlap, and it could be we want to define the values of x that are in both of those. So this will be an AND situation. We want x to be in the set minus 3, or the interval minus 3 up to 1, and from minus 1 up to 3. And so we can denote that as x is a member of the set from minus 3 to 1, and, or intersecting with, from minus 1 up to 3. And that's the intersection sign, meaning and we can conclude in this particular case that x is a member of the set from -1 up to 1. Notice both ends become square because those relevant ends of the intervals are point included. Okay, going back to domain and range and restricting the domain, we may want to restrict the domain for reasons other than making a function one-to-one. For example, a function may only apply to a certain set of values, particularly if it is being used to model a real-world situation. So if we have a function f of x is 4x minus 3, and the domain is from 1 up to 4, including 1 but not including 4, then what will the range be? Now notice we're using capital D with a subscript of f, means the domain of the function f, and we're using capital R for the range of, and then subscript f. So that's the range of f. Now we must in these circumstances sketch f because we can't be sure what's going to happen. So we have the axes and important points, so we've got 1 and -3. -3 is there because if we put 0 into this function we would get -3. We have 1 on the x-axis because that's the beginning of the domain, and if we put 1 into the function, 4 times 1 is 4, take away 3 is 1, so it's going to go through the point 1, 1. So there is our line. So that's f of x with no particular domain, or the whole of the real numbers as the domain. The domain goes from 1 and that is included, so we put a red filled in circle at 1, and it goes across to 4, so we need to map 4 through the function. So 4 times 4 is 16, take away 3 is 13. When we get to 4 in the domain, we don't quite get there, so we have an open circle, and then we can join them up. So that now represents that function. That is the graph of that function, and from the sketch we can see that the range is from 1 up to 13, square brackets on the left, round brackets on the right. So in that example you may think the sketch wasn't that important. We can see that actually we got the range by just applying the function to the values in the domain. We did the function applied to 1 and the function applied to 4, and that gave us our range. But we must be careful, as it says. In this case we were able to apply our function to the endpoints of the domain to find the endpoints of the range, but this will not always be the case. Let's have a look. If we think about this function, g of x is x squared minus 4x plus 3, and the domain of g is from 0 to 5. Okay, we'll go through the same sort of process of sketching. Here's our axes. Now we've got those values. Why are they there? Well, if we put 0 into g of x we get 3, so that's why we have the point 0, 3. We also, you might be able to see this, but we'd perhaps be scribbling with a pencil at this point, but we can perhaps see that x squared minus 4x plus 3 is the same as x minus 1 times x minus 3, which means we're going to have roots at 1 and at 3. So having identified those points, we can just draw a curve through them, and now we can start to identify what that means in terms of this domain that we've been given. So we need to find where 5 maps to, and it maps to 8. 5 squared is 25, take away 4 5s, which is 20, gives us 5 plus 3 is 8. And we're going from 0 up to 5. So we have both ends are included because we've got square brackets, so we put one end there, the other end there, and we can join them up. Now, if we just used the images of the endpoints here, we'd go badly wrong, because we would say that the range was between 3 and 8. The y values for those two endpoints are 3 and 8, so we could say the range is between 3 and 8, but it clearly isn't. In fact, the lower end of our range in this situation is given by the minimum, and that happens to be -1, which you could work out using your knowledge of quadratics, and this gives us a range from -1 up to 8. So be very careful with working out ranges and domains, certainly with working out ranges from domains, because tricky things can happen.